Here we're going to discuss geometric similarity and what it means for objects to be geometrically similar. And we're going to, in particular, see as objects are scaled up, what happens to their volume, what happens to their surface area, in 2 dimensions, what happens to their area. We'll start with the 2-dimensional case, and then we'll talk about the 3-dimensional case. So first, we have some definitions. Objects are said to be geometrically similar if they have the same shape. They don't necessarily have to have the same size. If they do have the same size and they're the same shape, then they are similar. We won't really talk about that. But geometric similarity, 2 objects are geometrically similar if they have the same shape. Now, how could we tell, just given 2 objects, if they have the same shape? Well, we're going to look for the linear scaling factor. The linear scaling factor is the ratio of the length of any part of the second object to the corresponding part of the first. And it says of any part. For certain shapes, you could have several parts to consider. Here we're going to talk about rectangles and squares. So how can we use this linear scaling factor to determine whether objects are geometrically similar? Well, let's look at these 2 examples. And the question would be, are these objects geometrically similar? And if so, what is the linear scaling factor? That's a lot of words. I'm not going to write that. Just going to draw 2 shapes. A rectangle, we'll say it's 5 by 7. That'll be shape 1. Shape 2, not necessarily drawn. That's not going to fit on the board. Well, we're going to do 2 examples. Maybe I'll do it like this, and then I'll see where the other example goes. So let's take a 5 by 7. Let's take a 10 by 14. Question, are these geometrically similar? If so, what is the linear scaling factor? Well, to determine if they're geometrically similar, the linear scaling factor is going to have to be the same for any pair of corresponding sides we choose. So here we have 2 different side lengths to consider. These other 2 that aren't labeled, they are also 7, 5, 14, and 10. But since it's a rectangle, the only lengths which are different, the only lengths which are different and not the same, the only lengths which are different in different ways are this side, 7 and 14, and this side, 5 and 10. So are these geometrically similar? Well, to determine that, we'll check the linear scaling factor. Let's pick this first vertical side first. Linear scaling factor. What are they for the first side? 14 over 7, which equals 2. So if we get 2 for the other side, then these are geometrically similar. For the second side, we have 10 over 5, which does equal 2. Since these are the same, these objects are geometrically similar. In a moment, we're going to talk about how area scales up. While I'm writing this next example, maybe you can think about how area scales up there, and in particular, how it relates to the factor, the scaling factor. Question, example, are these geometrically similar? If so, what's the linear scaling factor? So here I have 2 different linear scaling factors. Maybe I should have written as a theorem, if these are the same for all pairs of sides you can choose, then they're similar, and the linear scaling factor is that number. I'll just leave it like that, that's fine. Are these objects not necessarily drawn to scale? Are these objects geometrically similar? What were the numbers I chose in my notes? 10 and 21? Yeah. So these objects over here are geometrically similar. I'm going to write the answer to this example on that same third board by erasing this. So here, to determine if these two are similar, we're going to again find the scaling factors. First, we have a 21 over 7, which is a 3. So if you get a 3 for the other side, then they are similar. But notice here, we have 2 as that linear scaling factor, 10 over 5. So these are not geometrically similar. Now, to this point, most of you probably have seen similarity before in the context of triangles. The same type of linear scaling argument would apply to triangles. You know, they're similar if you can get the same ratio for any sides. And then with triangles, you do have a bunch of rules, side, angle, side, and so on, which you can use to determine similarity. I might put something about triangles on the worksheet. But next, I'd like you to observe how area scales up for similar objects. For non-similar objects, it doesn't really make much sense to compare the areas. But question, how does area scale up? Or we'll say question. What happens? Here I'm going to remark linear scaling factor equal 2. So question, what happens to area as an object is scaled up? Well, another way of saying that, you could compare the areas. You know, this is area 35, area 140. 140 is 4 times 35. You could do an argument like that. But I'm going to do a visual argument instead. I'm going to take the larger object, the 14 by 10, and see how many of those 5 by 7s fit inside of it. Well, here, if you divide that 14 into 2, you have a 7 and a 7. Here, if you divide that 10 into 2, you have a 5 and a 5. So notice, we'll notice 4 5 by 7s fit inside a 10 by 14. You know, don't worry about, you know, the one side going first versus the other side. That'll matter for something else we talk about, but not here. So notice 4 of those fit inside. Well, this can tell us how the area scales up. So here we have a 5 by 7. Here we have a 5 by 7, 5 by 7, 5 by 7. And we'll record this as, I think I need a definition first. Let's do a definition and then I'll write a theorem. Definition, what happens to area as an object scales up? We have a linear scaling factor over there. We also have an area scaling factor. So the area scaling factor is the ratio of the area of a scaled up object. That says object. So this should say, the only time it makes sense to talk about the area scaling factor in our context is for similar objects. So now I'm not going to write for similar. We'll assume we're talking about similar objects. The area scaling factor is the ratio of the area of a scaled up object to the original. So here, in previous, I'll just say here, meaning here, the area scaling factor, is what? It's 140 over 35. So do I call this a letter? No, I don't. Which equals 4. So you could see that by comparing the areas directly, or you could see that by fitting objects into, fitting the smaller one into the larger. But the question that arises is, can we determine the area scaling factor just from the linear scaling factor? You know, linear, 1 dimension, area, 2 dimension. They're both scaling up, so you might think that they are related. And here, linear scaling factor 2, area scaling factor 4. Well, I'm going to give the result and then illustrate it. So 2 and 4, you know, one is 2 times the other, one is the other squared. So it might not be obvious if it's a square or if it's a multiple of 2 in going from the linear scaling factor to the area scaling factor. But I'll tell you the theorem and then we'll look at it. Theorem. The area of a scaled up object goes up in proportion to the square of the linear scaling factor. So it is the square. There's some notation we could use for this. I'll write it down. So let's say area is proportional to the linear scaling factor squared. And I'm not going to use that notation other than just stating the result. But in this example with the 10 by 14s and the 5 by 7s, the linear scaling factor between the two objects was 2. The area scaling factor was 4. So you could have used that theorem, if I mentioned it, to determine how the area scales up just from the linear scaling factor. But let's ask another question about this example. How many square feet are there in a square yard? And this one's going to illustrate why it's a square rather than a multiple of 2. The first example didn't necessarily illustrate why it was a square rather than a multiple of 2. So how many square feet are there in a square yard? Well, I'll provide 2 solutions. Solution 1. Using this result, how does a square foot, well, how is a square yard scaled up from a square foot? Well, here, the linear scaling factor would be 3 yards in a foot. So the area scaling factor, this is asking about area, square foot. So area scales up by 3 squared, which equals 9. So this is purely using this theorem. But what if we tried to draw this out? I'll call this second one solution 2. Well, let's draw a square foot, and let's draw a square yard. There's a square foot. It's 1 foot by 1 foot. What's a square yard in terms of feet? Well, a square yard in terms of feet is 3 feet by 3 feet. So how many of these 1 by 1s fit in this 3 by 3? Well, 1 divides into 3 times. And now we have 1 by 1s everywhere. So notice I would like to write this under, but I don't think I have enough room for it there. So I'll just say there are 9 square feet in a square yard by that diagram. So we have this first result that describes how area scales up. The next question that arises is, how does volume scale up? Is there something that happens that's similar? Well, let's consider an example. I'll consider the example before erasing. Consider. I'm going to do this across 2 boards like this. Consider a 2 by 2 by 2 cube. Well, let's draw a 2 by 2 by 2 cube. So there's a 2 by 2 by 2 cube. I'll just say they're all 2s like that. Scale this up by a factor of 3. So I'll say scaled up by a factor of 3. Meaning here L equals 3. So maybe I'll say that. Scale up by a factor of L equals 3. Because we have been using L for that. Well, what would that look like? Well, scale up by a factor of 3. Instead of a 2 by 2 by 2 cube, we're going to have a 6 by 6 by 6 cube. So let's draw a 6 by 6 by 6 cube. So here we have a 6 by 6 by 6 cube. So what we want to do is compare the volume of the first and see if we can see that in terms of the linear scaling factor. I probably shouldn't have erased that first board because the next result I could have just used what was written there. That's okay. So how many of these 2 by 2 by 2s fit in this 6 by 6 by 6? Well, what we're going to do, maybe I'll use a different color. What we're going to do, let's fit some 2 by 2 by 2s in. 6 divides into 2 3 times. Or no, 2 divides into 6 3 times, I guess you should say. So let's divide each 6 by 6 by 6 into 2 by 2 by 2s. So right now, if you just take this first, this frontal square, these are all 2 by 2 by 2s. Because we took a 6 by 6 by 6 and divided it up into 3 even things. Let's do that with all of this object. And when you're doing one of these, I always think of drawing parallel lines for these slanted ones. Lines parallel to, the one you're looking at. Like, so for this next one, we want them parallel to this black line. And similarly up here. And then down here. Some of you may have studied art, and what I just said is obvious in some classes. It has something to do, I don't know if it's related to that 2-point perspective thing. It probably is. I'm trying to remember. I learned 2-point perspective for like 2 days in 11th grade in high school. I wasn't that good at it. But I did actually think of that in terms of things like that cube. Well, anyway, we have now divided this 6 by 6 by 6 into 2 by 2 by 2s. So these are all now 2s. I'll just label a couple of them. These are all 2 by 2 by 2s. So how many 2 by 2 by 2s are in this 6 by 6 by 6? Well, let's take this top layer. So just this top layer. Well, in this top layer, here's one. There's a 2 by 2 by 2. Here's another. Here's another. Maybe I should have done this one. This one looks just like it. Yeah, I'm going to do that. So right here on this first corner, you can see, maybe I'll even put the 2 over here so it looks even more like that. In this first corner, right here, we have this 2 by 2 by 2. So right there we have a 2 by 2 by 2. Well, we also have one here. We also have one here. We also have one here. So here's the top of it, and then under it there's more of a cube. We have one here, 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 and here. So notice in that top layer there are 9 2 by 2 by 2s. Well, that's just going to keep happening for each of these 3 layers. So we have 9 2 by 2 by 2s, we have another 9 2 by 2 by 2s, we have another 9 2 by 2 by 2s. So we'll notice there are 27, 9 times 3, 2 by 2 by 2 cubes in the 6 by 6 by 6 cube. There are 27. Well, our goal was to see if we could relate this number down here, 27, to our linear scaling factor of 3. Well, 27 and 3 are nicely related. So we defined the area scaling factor. I'm not going to formally define the volume scaling factor. It's the same thing, just with volume. But we will record this as a theorem, and I'd like it to be phrased the same way as the first theorem. The volume of a scaled up object goes up in proportion to the cube of the linear scaling factor. And with our notation, we would have V is proportional, V, the volume scaling factor, is proportional to L cubed. So we have a result on volume. We have a result on area. I don't think I wrote this in my notes. Yeah, okay, I guess I sorted it. One other scaling up we're going to look at is surface area. What happens to surface area as we scale objects up? And to do that, I'm going to consider, I think it was 1 and 3. I just looked at my notes, I can't remember anything anymore. Yes, 1 and 3. We're going to consider a 1 by 1 by 1 cube, and we're again going to scale it up by a factor of 3. Consider a 1 by 1 by 1 cube, scale it up by a factor of 3. Well, you scale it up by a factor of 3. I'm just going to redraw this. That's a nice drawing, but I don't really need to divide up the sides to consider surface area. Scale this 1 by 1 by 1 by a factor of 3, and we get a 3 by 3 by 3 cube. And we're going to compare the surface area. So before, I didn't compare the volumes directly. You could have compared the volumes directly. You'd get, what, 8? And for the volume one, you'd get 2 by 2 by 2 volume 8. 6 by 6 by 6 volume, I think it's 216. And then you could do 216 divided by 8, which is, yeah, it's 27, because 240 is 30, times 8. But here, we're going to directly compare the, or we're going to not fill in the surface area. You could do it by filling in the surface area, dividing this up, dividing this up into squares and comparing the surface area like that. But instead, I'm going to compute the surface area directly. So here, what's the surface area? Well, what's the surface area of a cube? Well, the surface area of a cube is the one side plus the other 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 side. 6 sides, about 6 faces, I guess you should say. 6 faces to consider. But for a cube, all of them are the same. So here, we have 6 squares areas to take. So here, this first square, area 1 by 1, which is 1. The second square also 1 by 1. All 6 squares are 1 by 1. The area of a 1 by 1 square is 1. So the surface area of this first one is 6. What's the surface area of the second one? Well, we again have 6 faces to consider. This first face, maybe I'll fill in so it's clear what I'm taking the area of. This first face has area 9 because it's a 3 by 3. And all 6 faces have an area of 9. So the surface area, 6 times 9, is 54. Well, yeah, okay, I guess I'm going to erase this so it follows the sequence. I was hoping I could jump over to this board and then use this, but I'll just erase it and rewrite it for surface area. So notice, the volume scaling factor, you could do 3 cubed, which is 27 here, or you could divide the, so I'll say, or the volume of the second, 27, divided by the volume of the first, 1. So the volume scaling factor, you could use that theorem, or you could compare the volumes directly. Either way, you get 27. What about the surface area? I'll say V equals that. Surface area scaling factor. Well, we don't have a theorem yet on surface area scaling. So all we can do is compute it directly. So I'll say surface area scaling, I'll just call it SA. The larger one is 54, the smaller one is 6. You could do a parallel argument for a scaling down. I'm just going to, let's just stick with scaling up. The surface area scales 54 into 6, which is 9. So theorem 9, how does, the question would be, we're not going to ask how does surface area change with a linear scaling factor. That's less interesting than comparing the surface area scaling to the volume scaling. So just thinking, aside from this class, just think, we have an object, we're scaling it up. What happens to the volume? What happens to the surface area? How are they related? Well, this argument suggests as you scale something up, the volume is going to be increasing at a rate much faster than the surface area. This volume went from 1 to 27. The surface area went from 6 to 54. And that is true. In general, the volume will scale up much faster than the surface area. But what's also true is possibly more interesting. The volume scaling and the surface area scaling are related. So surface area scales, how do I phrase it, as 2/3 the power, so not multiplied by 2/3, 2/3 the power of the volume. I'll just say 2/3 the power of the volume. Man, it's scaling factor in now. Okay. Surface area scales as 2/3 the volume. 2/3 the power of volume. So example. In previous example, the volume scaling factor was 27. So the surface area scaling factor would be 27 so the surface area scaling factor is 27 to the 2/3. What's 27 to the 2/3? Well, I don't know 27 squared. Actually, I think I do. I think it's 729. That number shows up a lot. But instead of doing 27 squared, let's do 27 to the 1/3 first. 2/3 is 2 times 1/3, but 2/3 is also 1/3 times 2. You can multiply in whatever order you want. More on that in 2 videos from now. 27 to the 1/3 is 3, the cube root of 27, and 3 squared is 9. So we could have used this theorem to find this surface area scaling if we had it. But you could also see how that relates to the original cube.